How about now? There we go. Shoot. I had it off because I was going down there to the anyway. Yeah, there you go. Let's see. Is it working? It's working. All right. So don't get me wrong. This is a good thing, but it's still not design. It's still analysis, and because of that, I'd prefer if you're interested to get deeper, just go take that course. Um, and what I'll do is just go on from here into the next section, which is what I started with those guys this morning. And what we did is, imagine you're stuck on a rigid link. And in this particular case, if you're stuck here at this point here, if you're stuck at this point and welded there, no matter what motion is happening, so if this thing goes this way and this thing goes this way, and say it ended up, or say it went like this, so forget that one, then actually it sort of rotated. So if you're pinned right here and you look down here and you see B, it appears like it's rotating around you. But then again, you may be moving somewhere, but you're not aware of that. You're welded to A, looking at B. That's what this equation, that's what that term is. This is your displacement or your location. That's their location. This one is you sitting at A, staring at B. What do you see? If it's a rigid body, the only thing it can do is rotate one way or rotate the other way. So if you think about it like that, here, let me get rid of all this junk. You move on down, then yeah, who cares about these two? This is due to a rotation about A. So you're sitting at A, you're staring at B, it only looks like it's rotating. Well, this one's due to the translation of A and the rotation around A. So you should have said more about that. And then you move on, well, then obviously you take the derivative. Okay, here he's showing some pictures. Okay, so for example, I mean, I didn't say much about this. I guess I should have, but here, I'll say it now. So if you look at this thing, this part right here is as if it just translated. So that and that are the same. And then you start looking at it and you say, hey, wait a minute. It didn't actually do that. It moved to here. So then, in fact, you're pinned here. You see it rotating like that. And that's essentially what's happening here. Let's see if I can get all this junk off. So then what he does is, that's the differential. Then he takes the time derivative, okay, which that's the next step. And you see that. Now, if this term is completely associated with rotation, then, and it's rigid body, then you could do this, r theta dot u theta, but that doesn't do any good. But you can do the omega. Here, might as well just go down to the next page. I mean, you don't want to present it like that. You want it in a general form. So you want it like this. So this, in effect, is like the term r theta dot. There's your r, your theta dot, your omega. It's just a cross product. And so, and the cross product's convenient, because, let's see if it gets right. The mathematics of doing it is fairly straightforward, and we'll do some of that in a minute. So if you want to know what's happening, this is pure only rotation. That's some movement, and this is a movement as the result of the movement here plus the rotation about that. And so what I did then is I went in and let's see, did I pick a problem off? I think I monkeyed with this problem. So let's go look at it. this shows a difference in the way I think, in the way the book thinks. So what I started doing, and here I'll do a highlighter to kind of, I drew this vector out. So the first thing I did is, of course, I dropped the picture on here. And then I said what he's looking for. He wants to know the velocity of B. And I decided near the end of the lecture, I wanted to find the velocity of C as well. So I wrote the equation, velocity of B is equal to velocity of B relative to A plus the velocity of A. Now, he actually told us exactly what that was. So I just wrote it down. Once I wrote it down, I'm like, okay, well, I can just keep copying this thing, and you can see it reappear. But then I have this pure rotation. This is if this velocity, this funny thing right here, is as if somebody glued me to A and forced me to stare at B. And in fact, what it is it appears to be just a simple rotation about it. And if you come down and look at it, what the cross product is, you just fill out the omega and you fill out the R. So this means I have to go find R, which in the lecture, I did that kind of after the fact. I drew a vector from A all the way to B right there. Does it pop back? No, it doesn't. So here. And then I wrote it down. It's a length 0.2 and it's 45 degrees. So it was 0.2 over square root of 2 and minus 0.2 over square root of 2. Pointed to the right and down. So to the right is positive I, down is negative J. So I just took that thing and I said, well, I'll just slip it right in here. So I slipped it right in there. It was all fine. Then I did the cross product. And what happens in these cross products, and I sort of carried this out, 00WBA is the rotation. Okay, good question. So, and I should have mentioned that a little bit more. When you have planar stuff, which most of the stuff we've got is planar anyway, it's lay it out on a coordinate, and this is implied. Okay, so positive is this way, positive that way. A rotation is positive I cross J. So that's a positive rotation. So in fact, what it is there's no rotation about this axis. There's no rotation about that axis. It has to rotate in the plane, but I don't know its value. I have no idea what WBA is. So I just got to write it in. Now I always assume them to be positive. So I don't have to keep up with anything. I just write a number. If it comes out to be negative, I just say, well, instead of rotating it this way, it looks like it's rotating that way. So then what I did is I sort of kept that one, the VA by itself, over to the right. And then I slid down, and I think I did it correctly. I hope I did it correctly. I pulled this thing out. Where'd it go? Okay, so I pulled this. I pulled the I off. 0, this term, that term, and that term. So I got something and something. But this was a nothing. Okay, so I should say nothing and something. A negative, which ended up with, okay, let's make sure I got this. This one should be that one. So that little blip right there is a negative. So a negative of that gave me a positive. Then I get a negative because I took the positive, negative, and so on. So pulled the cofactor of it, and it's this one and this one and that one. Now the K didn't show up because the cofactor of it is this. That's what my little arrows were. So it's 0 across here, so it never shows up. So it is nothing times a minus something with a minus in front of it ends up that way. So I get this funny number, that number, and there's the 2 still, minus 2 still hanging, just hanging. Yeah.
So if they gave you rotation about like that axis, so they gave you the value of WBA, how would they word that?
They just tell you it'd be so many radians per second, and then probably put a little vector, oh, so many radians per second like this. And that's all they would say. And so you would look at it and say, was it like that? That's positive. So you'd put in positive. You got to be careful there, because if it does like that and you put in positive, you're going to show the total exact opposite of the velocity the other way. So you got this. And then the question was, and this is where I stopped and interpreted that. And interpreting this is what I did. I sat down, or I copied this thing down, and I said, well, what does this mean? This means I'm stuck. Somebody glued me to A, and I'm staring at B. It looks like it's rotating. So if I'm stuck there and I look at that, that looks like that's rotating. That's the velocity of B relative to A. Turns out this component goes to the right, and it comes up. Now ignore those two right now. Hang on. Let me erase those two. So, and what I'll do, because that's another whole issue there. Here, let's go away. And I'll come back with a red marker. So that is in fact that. And is it perpendicular? Yeah, it's perpendicular. It's the same distance here as it is there. So that's the way to interpret just that one by itself. That's the velocity, as if you were sitting on this, watching that rotate. And then what I said is, well, let's take this 2 meters or meters per second and just copy it down here and attach it. I add this vector to that vector, and I'm supposed to get that vector. And that's where I did this. I sort of drew it, and I said, well, oh, shoot. Did I not? Oh. So I drew it, and I said, here it is. So I add this one to V. This is a trick question. I said, well, here's the velocity. Then this has to be velocity of B. And I said, what's wrong with that? If you recognize what's wrong with that, you see the next key. And the next key is this point B has to slide along that slot. It's forced to slide along that slot. So that can't be. This has to be the answer. It has to come all the way down exactly to right here. And it comes over here. So this is velocity of B. This is velocity A. And that's the only way that vector diagram works out. Now, with that in mind, that tells you if you make omega higher, this becomes longer, and then your 2 gets dropped out there, and that's not right. So you got to make the omega right such that this value of 2 exactly puts B right there. So how do I get rid of that? So hang on. So that being the case, then what I did is I said, if that is the case, velocity B must go along the slot, then it has to look just like that. And so it has to be some number in the I direction. So I can just copy that down. So then I copied that down to here. Over here was the relative, me being glued to A looking at B. And here's what A is. Then what you notice is hey, well, wait a minute. I can break this down into 2 components. I'll look at the I term and get this equation. I look at the J terms and get that equation. I get 2 equations, 2 unknowns. I take this one and I can solve for WBA, which ended up being positive 14.14 plus some digits. Then what I did is I took my 14.4 and stuck it in here and ended up getting back a 2. And one person said, hey, wait a minute. I could have told you that to begin with. Because if you look at the drawing and it's 45 degrees, then this is 2 and that's 2. So that 45, but then he was like, how do you do it for all instances? And that's where I got into discussion of that other course again. And so the next thing, so does this part make sense so far? Because then the next thing was, okay, now that you recognize that would be 2 and this would be 2, what about the velocity at c? And then what I did, let's see, I don't know if I did it below it. Yeah, I did do it below it. So vectorially, it looks like this. Well, okay, how do I slide? Okay. If you look at this, okay, if this is the velocity of B relative A, and that's 2, and that's the velocity A, it turns out that this is the relative velocity, as if I'm rotating about point A. So this is the velocity of C relative to A. If you're stuck on A, staring at C, that's what you see. But it's rotating faster than this one. This one's going faster. And then I just copy this vector down, and I get, this is the velocity of C. And vectorially, that's what this is. So this is actually velocity of A. And then mathematically, I just go through the motions. And what the motions are first, velocity of C relative to A, this value is larger. Now I know the omega from the last problem, but the link out there from A all the way to C is now 0.1 plus 0.2, so I end up with 0.3. And I multiply those out, and this is the part that's the relative velocity. Me being stuck on A, staring at C, there's the velocity of me, which is I'm stuck on A, add them together, and I get the velocity of C. And I think I just stopped right there. And I don't know what, that was just, I don't know what I did. There was, oh, there I'm just, I don't know. Oh, I know what I was doing there. Okay, I probably should. Okay, so I should go back and talk about that for a minute. So does everything make sense? And now here's one of the things I make a big deal about. Where'd the book go? This is what is very annoying to me. This book, Statics and Dynamics, it's almost like they were written separately and not melted together. Remember in the moment, R cross F, and we did a lot of R crossing F. And now he's not doing that as much. He's breaking it apart. So here's the part that really annoys me. To me, I would set that up, I, J, K, just like I did in 0, 0, omega, and then some value for R, some value X, and 0. But what he's doing is he's saying, let's look at the first term. He's saying omega times 0.2 sine of 45 times K cross I. So that makes you have to stop and think, well, wait a minute. If I have, here's Z, X, Y, Z, so K, which is this way, cross I, oh, wait a minute, that's J. So in fact, he gets that. But you have to stop and think about that. So you have to stop, cross I with this, cross K with J, cross this and that. To me, that's an unneeded and unwanted distraction from the problem. To me, I would just as soon put them together. If you ever want to know, that's what I was doing right there. Is I was saying, hey, if you look at this and say, I want to know the first row is actually a vector that is J. The second row is actually a vector that's I. So J cross I is minus K. So to me, it comes out in the wash. If I just list it out like this, it always comes out in the wash. And I never have to sit there and think, okay, wait a minute, what's cross what? It just always works. So to me, instead of working the problems the way he does, I don't work them that way. I set up the little determinant, and then I stare at it and recognize some things about it and go with it. Now, I may not be the only person that does it, or I might be. I don't know. There you go. So I like to reduce my probability of making a mistake at all costs. And I think that's one of them. So let's go do another problem. Okay, this is a good one. So the collar moves downward with the velocity of 2. Determine the angular velocity of link CB. The C? So let me get a good picture. So he wants to know the angular velocity of CB. So here, snippet should be there. I will copy this thing. Now, the only reason I'm doing these is to accentuate the fact that I don't do the way he does it. And then I'm going to work regular problems out there. Okay, add a page, drop the thing. Okay. So the way these sequences work, I can work from C to B down the link and from B to A. Now I'm going to ask another question. I'm going to say, if that's the case, what's the omega AB as well? So first thing I should do is list X, Y, and this is positive. Okay, so I know this doesn't seem right. Well, in this case, I'm sorry, in this case it kind of does. That's positive omega AB. So, all right, so all you do is you say velocity of, it doesn't matter which one you do, velocity of B is equal to velocity of B relative to C plus velocity of C. Or you could have written it this way. The thing is, it really doesn't matter because that's the opposite exactly of that. So whichever way you did it, doesn't matter. But then the next thing is, okay, wait a minute, that looks funny. The next thing is, which one do we want to do? It doesn't matter. I'll just do this one. I don't need too many equations on the page. But then I'll do this. Velocity of B is equal to velocity of B relative to A, plus the velocity of A. Hey, that is pretty straightforward. That's 0. So from this, I'm going to get something interesting. And I'm going to go ahead and do it. Velocity of B is equal to omega AB cross RB to A. Okay, now I'm going to sort of get rid of some of the stuff here so I can draw pointing a vector, which does exactly like this. That vector right there, well, I could say plus 0. This vector is nothing more than minus 0.2j. That is that vector. And I'm going to assume that this vector is just omega AB K. It comes straight at you. It's rotating, what is that, counterclockwise. And so I'll look at this thing, and then I'll say I, J, K. Now what you're going to get out of this, you're going to say, duh, but. And then I have this one, have nothing there, minus 0.2, and nothing. And now if I go down a little bit more, maybe, so my velocity of B is going to be, stare at this a minute, and you'll realize if I look at the J component, I don't get anything, or the K component. All I get is this, or 0.2 omega AB in the I. Now, does that make sense? And let's see if I can make heads or tails of that. First of all, I'm assuming always that's positive. So I'm rotating like so. This means I already know this velocity's got to be like that. It's got to be this times that. And it's in the positive x direction. And in fact, that's what I get. So you could have looked at it and said, duh, but you didn't. And I was supposed to go through and do this. So the next thing is I'm going to take the picture. I'm going to go down, the picture down here again. And now I'm going to work on the second one. The velocity of, I don't know which one I should do. Velocity of B is equal to the velocity of B relative to C plus the velocity of C. He told you what that one was. So that one's nothing more than minus 2J. And this one's going to be omega BC crossed with RB relative to C. Now the velocity of B is nothing more than, and I'll go ahead and put it in, 0.2 omega AB times I. So this part came from the previous part. So now I just got to fill this out. I, J, K, minus 2J. Now, the next thing I should have done, I should have taken a break and drawn out this thing, a vector that starts at C, points down here to this. Well, that's pretty easy. So that RB relative to C is equal to 0.2I minus 0.2J. So if that's the case, and actually, here, I'll move it over. Let me split these 0.2 omega AB I. So now I put in put in 0, 0, omega B, C. And then put in 0.2 minus 0.2, 0. Now, what do I do? Well, I see. End up with 0.2 omega AB I equals 2. And I'll end up with an I component. And I'll end up with a J component. J component minus 0.2 omega BC 0 and then minus 2J, because there is no K component, because this times that is always 0. If I do this, let's see, and I'm going to expand it out. 0.2 omega AB I equals 2. That times a minus that gives me 0.2 omega BC I, and in here. And then this one minus that one is plus 0.2 omega BCJ minus 2J. Now, I'm going to stop and try to interpret this before I do anything. This term is the velocity of B as if you were sitting on A. Take the picture again, drop it right here. If you were glued to C, and you were staring at B, and it was rotating in a positive sense, X and Y, positive sense would be that. If it's rotating like that, the velocity is going that way. So it would be a positive component, positive component. That's what I get. And they're equal. They're 45 degrees. So I'm comfortable with that so far. So physically, you could interpret it that way. And this one would be I, and it'd be 0.2 omega AB equal 0.2 omega BC. So they're both the same. And then the J component ends up being 0.2 omega BC minus 2 equals 0, or omega BC, which is equal to omega AB, which is equal to 2 divided by 0.2. What is that, 10? No, I don't know. Yeah, that's 10. And that would be in radians per second. Let's see what he comes up with. So he comes up with that 2. And what is he saying for second one? That's really not fair. But I guess it's okay. I identified that VB there was a rotation associated with that. And he just identified it as only going like that. So he identified it as being only to the right, found out it, and then he found this. But since that's the case, that you could back out the other one as well. So, oh, there's more. Okay, so so that's pretty much it. There's another, let's see, it's got 5 minutes left. I'm not sure whether it's worth doing another one. What do y'all think? You want to do another one, or you want to just go ahead? You want to go? Okay. Well, you also have the other lecture, which I kind of sped through it. But the thing is we'll be working tons of these over the next period, so a couple of periods. And then we'll be going into instant centers, and then how you do the accelerations are the fun ones. Those will be exceedingly fun. And this is where they start. And then you end up with an extra term right there. So we'll go ahead and go and then reconvene. I'll be back here at 11. Day after tomorrow. Guess the day after tomorrow's Friday. So I'll be back here at 11 and then again at 1 and then again at 2. But you only care about 11 and 2. Yeah, just 2. But if you come in at 2, I'm sort of taking it upon myself to review what I did the last time for a few minutes.
We all have circuits, right?
Oh, do you? So where is your circuits at? Oh, it's all the way in Corley. Oh, okay. Okay. Well, I've got statics right before this too. So part of the